today's Future Ocean Forum. I am Liu, coming from the group of Professor Dong Wang in the Ocean University of China. He has authorized me to host today's seminar. It's our great honor to have Professor Conleth Loughlin here, and he is a world-renowned scientist from the University of Western Australia. Before we commence, I would like to take a moment to provide a brief introduction to Professor Loughlin. Conleth Loughlin is a geotechnical engineer and scientist with extensive research and industry experience, specializing in the geotechnical aspect of offshore energy developments. His research focuses on the safe and sustainable development of the world offshore energy reserves, particularly offshore renewable wind energy. The research has been supported by 37.9 million Australian dollars in funding, leading to more than 200 research outputs. In his role as the UWA, he is a professor and director of the National Geotechnical Centrifuge facility and the deputy head of school for the UWA School of Earth and Oceans. The NGCF is the flagship research infrastructure facilities for UWA, globally recognized as setting and maintaining the highest standards in geotechnical centrifuge modeling. It has underpinned UWA's research success and impact in offshore geotechnics, and with a high level of demand from within both academia and industry, has been heavily utilized by the global offshore industry for the design of infrastructure and foundations. Okay, the theme of his talk today is geotechnical challenges in offshore wind energy developments and the role of centrifuge modeling in developing solutions. Now let's welcome Professor Loughlin to give us the seminar.
Okay, thank you for that. Just let me share my screen, or just sent a request to share it.
Yeah, I can see the screen. I can see your PPT.
Excellent. All right, well, thanks for the introduction. And as you mentioned, what I'm going to be talking about today is offshore wind energy, geotechnical challenges, what's different about offshore wind energy compared with more conventional offshore energy types, and where can we use geotechnical centrifuge modeling to help in developing some of the solutions for the rather unique problems that offshore wind energy brings. Okay, so what are these geotechnical challenges facing the offshore wind industry? Okay, so from an offshore geotechnical design perspective, and relative to oil and gas, where I suppose most of the offshore geotechnical engineering knowledge and state of the art comes from the perspective of the two different types of energy developments, an oil and gas structure versus an offshore wind turbine, the first thing that we can say is the economic returns are much lower for an offshore wind turbine. That means that there's much more impetus to optimize the designs. There's also another aspect, is that on an offshore oil and gas platform is crewed by people. So the risk, or sort of the consequences of failure, are quite different to that of an offshore wind turbine, where there are not people on board. Typically, at least in today's developments, offshore wind is in relatively shallow water compared to the very deep water that oil and gas developments have been in. And in shallow water, you get much more variable and challenging seabeds. These are much more dynamic structures. They see much more energetic loading from and cyclic loading effects relative to oil and gas. And a very key design difference is the designs are governed by very strict displacement rotation limits, such that there's much more of a focus on stiffness rather than capacity. The other thing that's really quite different between oil and gas and offshore wind is that for an oil and gas development, you're generally talking about one structure or maybe a couple of structures. And the amount of seabed footprint that it occupies is relatively small. Whereas offshore wind developments are of the order of tens to maybe a couple of hundred of offshore wind turbines, meaning that it takes up a huge amount of seabed, and all of that seabed has to be characterized with geotechnical site investigation. So, for example, each wind farm development could comprise up to 100 foundations. For example, if they were bottom fixed and there was 100 wind turbines, that would mean there'd be 100 foundations. And if these were floating and with each wind turbine supported by on a 3-point mooring spread, that would mean about 300 anchors. If you compare that with an oil and gas development, you might be talking about maybe somewhere between, let's say it's floating, you may be talking something between 12 and 16 anchor points. So it's really a very, very different scale. So just picking up on that point about the offshore, so the seabed footprint of a offshore wind development, what I'm showing here is a map of some of the declared wind farm zones off the coast of Victoria in Australia. So if you are familiar with Australia, you'll see Melbourne here, which is on the south coast. And these developments here are the ones that have been declared as wind farm zones. There are no actual offshore wind turbines in Australian waters to date. What we have is a number of zones that have been declared for licenses that various developers have picked up on and that are developing. And this one here, which is mark number 6, is the Star of the South, which is a 2.2 gigawatt development. And that is very much likely to be the very first offshore wind farm in Australian waters. Now, if you're familiar with the map of Australia, you will quite readily understand that this is a huge geographical area. But what I've done, just for today's talk, is I've overlain this area with a map of close to where the Ocean University of China is in Qingdao. And you can just to give you a sense of the scale of the seabed that is that needs to be mapped with cone penetrometer testing, geophysics, sampling, etc. So this is really, really massive areas. It's very difficult to characterize completely. You're always going to have to make economic decisions on where to characterize, realizing that you may not have information at every location. And that means that because of the much, much larger spatial coverage or seabed footprint, there's going to be much less certainty on the seabed properties, and that factors into the design. This is a very useful infographic that came out of a study a couple of years ago from the University of Southampton, where they looked at just from a UK perspective and looking at UK 2050 targets for offshore wind. Or sorry, well, yes, for offshore wind, and they looked at say, well, what is the scale of activity that needs to happen to be able to realize these targets? So what you have here on the vertical axis is the installed capacity in gigawatts, and on the horizontal axis we have the year. Now these data were available up to about 2022. And I've just added on to this plot where we are today in 2025, and they're currently sitting at just under 15 gigawatts of installed capacity, slightly under what the trend line or what the sort of projected or extrapolated data would require for them to hit the target of 50 gigawatts by 2030. So already we can see that they're not quite on target. Okay, so if we then take this 50 gigawatts by 2030 target and bring it out to 2050, and it's just somewhat over the 50 gigawatt mark. But then if you add in all other types of, this is for domestic electricity, but if you add in hydrogen and hydrogen export, you can see that the potential amount of installed capacity could go up to almost somewhere close to 500 gigawatts. But if we focus just on the domestic electricity aspect of things, and here on the other vertical axes, we have the number of turbines that looks like in terms of offshore wind turbines, the number of anchors that would be required, assuming that these were all floating developments, the amount of seabed area that needs to be characterized, and therefore the number of CPTs or cone penetrometer tests that need to be completed. So just to hit those domestic electricity targets by 2050, we're talking about over 6,000 offshore wind turbines, almost 19,000 anchors, almost 25,000 square kilometers of seabed area that needs to be characterized, and that would mean about 28,500 CPTs. Now, the scale of this activity is completely unprecedented. It's not like anything we've seen before, and it really sets the scene for the amount of upscaling and uptake we would need to be able to achieve these targets. Just the number of geotechnical engineers that would be needed to service this kind of demand, the number of site investigation vessels that would be required, the amount of laboratories that would need to be doing, that would need to be in operation to conduct all of the element tests from the samples, etc. It really is a scale of activity that we haven't seen before. Okay, so getting back to, so that's sort of setting the scene in terms of the problem that we're trying to solve. So in terms of solving those problems, how can geotechnical centrifuge modeling contribute? So first of all, let's talk about what it is. So I might just worry that that's going to get very noisy. Hopefully it won't be too bad. So what is geotechnical centrifuge modeling? Well, for those that don't know, a geotechnical centrifuge is a swinging platform. On one end, you've got a counterweight. You can just see here with this little schematic. On the other end, you've got some kind of swinging platform. And if you've ever seen videos of astronauts training for space or space flight, they spin around in something like this. And the reason they do that is that when you spin around, you get a centripetal acceleration, making things feel heavier. And that prepares them for space. Okay, so why, from a soil mechanics perspective, would we do something like that? Well, the reason we would do that is that because geotechnical behavior is strongly stress dependent. So if we take a reduced scale model and do some experiments on the lab floor, we're at very low stress levels. And because the geotechnical behavior is strongly stress dependent, if we're at very low stress levels, there's a good chance we're on the wrong part of the stress strain curve, and the results that we get are going to be erroneous. How can we solve this? Well, if we spin the same experiment in a geotechnical centrifuge and spin it up to, say, for example, 100 times Earth's gravity, then that reduced scale model will have the same profile of stresses in that model as it would in the real world, but in a depth that is 100 times higher. So we can, in a reduced scale model, replicate the stresses over a much greater depth in reality. And that's the principle of centrifuge modeling. There's lots of different scaling relationships that come from that, but that is the key thing that we're doing. We're just getting the stresses right in the sample before we conduct our experiment. Okay, so at UWA, we have 3 geotechnical centrifuges. We have 1 drum centrifuge and 2 fixed beam centrifuges. It's in UWA, it's a very important piece of research infrastructure for us. It's been around for a very long time. The first beam centrifuge was installed in the late 1980s, and we're still going strong. It's the only such facility in Australia, and it's one of the busiest anywhere in the world. Most of our work over this last 30 years has been supporting oil and gas developments, but over this last, I suppose, close on a decade now, we're now focusing very much on offshore wind energy. So where are we? Well, if you haven't visited us here in UWA, UWA is on the west coast of Australia, where this star is in the city of Perth. Perth is a rather isolated city. It's closer to Singapore than it is to Sydney, but it does have some lovely weather all year round, and some very nice beaches and a nice city for those of you that may wish to visit us here. As I said, the facility itself has got 3 centrifuges. The one on the top left is the smaller of the 2 beam centrifuges. It's a 3.6 meter diameter 40G ton machine. That's been around since the 1980s, late 1980s. We then have this drum centrifuge facility, which was installed in the 1990s. And then about just almost 10 years ago, we installed a 10-meter diameter beam centrifuge, and all are actively busy today. Okay, so where did centrifuge modeling all start? Well, the initial ideas came out of France, a man called Phillips in 1869, but it wasn't until the 1930s that the initial tests occurred, both in the USA and in what was known as USSR at that time. And those were independent testing of these concepts. But it was a few decades later before really the initial generation of modern geotechnical centrifuges arrives in the 1970s to 75. Initially in the group of Rowe in Manchester and in Cambridge and the late Andrew Schofield, then in Liverpool, Osaka, Tokyo, and then Denmark. And if we look today, there is a technical committee under the ISS MGE, which is the International Society for Soil Mechanics and Geotechnical Engineering. So the technical committee for physical modeling and geotechnics is called TC104. And if you go onto the website, you can look at facilities and you can see it just taking a snapshot of the top part of the Asia Pacific region, where you can see UWI is the only Australian geotechnical centrifuge facility. And then there are lots in China, as you can see with the graphic here on the right hand side. I would say there's lots of facilities that have been installed around the world, but not all of them are active. I would imagine there's probably something of the order of around 50 geotechnical centrifuge facilities in the world that are actively doing research and producing output. In terms of international support, as I said, there is a technical committee, TC104, Physical Modeling and Geotechnics. It's got a dedicated journal, which is hosted by the Institute of Civil Engineers in the UK. And that journal is called the International Journal of Physical Modeling in Geotechnics, which is, the editor is now Xianfeng Ma in Tongjin, I think. We have an international conference, ICPMG, every 4 years. So the next one is in Zurich in 2026. And then we have regional conferences, Eurofuge and Asiafuge in between years. So the last Eurofuge conference was last year in Delft in Netherlands, and the last Asiafuge conference was in Abu Dhabi last December. There's numerous keynotes have been published on the role of centrifuge modeling and how-to books, including the very classical book by Taylor, Geotechnical Centrifuge Technology. For those that haven't seen geotechnical centrifuge, this is what it looks like. This is a package or a soil sample sitting on our 10-meter diameter beam centrifuge here in UWA. So you can see we have a sample container in which there'll be some soil, and on top of that you may have some kind of actuation which will be manipulating the model, whatever that model might be. And if we look at the images on the left and in the middle, in this case that model is a model monopile. So this one is about 50 millimeters in diameter, which would be a typical scale for a reduced scale centrifuge model. And then you can see here that the actuator is connecting to the model. There's a load cell in here. What we're doing here is we're pulling out the piles. We're measuring axial resistance, and the load cell is measuring that axial load. So that's what it would typically look like. In behind this fairing here, there will be a data acquisition system. You can see all of these sensor leads going off, so all the data needs to be acquired. Up in here, there'll be a control cabinet where we've got our motion control system, which is sending the signals down to the actuator to impart whatever kind of loading that is of interest in this case. Okay. So having covered that in terms of what the centrifuge is and how it operates, I'm going to now go through some examples of where centrifuge modeling has contributed to some of the offshore wind challenges and improving our design approaches. So the first example I want to look at is suction bucket foundations. So a suction bucket foundation can be used as a foundation for an offshore wind turbine. It's generally now used with a jacket structure, and you can see these jacket structures going along a barge past the city of Dundee in Scotland. And these are heading up to the Seagreen offshore wind farm off the coast of Scotland, which uses suction bucket jackets to support the wind turbines there. How they operate, or well, I suppose the motivation for using a suction bucket relative to a pile is that they're rather easy to install. You don't need to use a pile driver. You can just install them through a combination of their self-weight and pumping water from the interior of the suction bucket. That also means that you don't have to use a pile hammer. Pile hammers are tricky because they emit or they make a lot of noise, and those acoustic emissions can be harmful to marine mammals to the extent that there are quite often limits on the amount of noise that can be produced when you're doing a pile installation, and it can be quite costly to mitigate or to suppress those kinds of noise. That kind of noise. So you can see here in the bottom left a little schematic showing you how it all operates. So the suction bucket is lowered to the seafloor. There's an opening on the lid of the bucket, allowing the water to escape. And then whenever the bucket comes to rest at some self-weight embedment depth, then a pump docks onto that the lid of the bucket, and it starts to pump water, as you can see here, pumping water out from the interior of the bucket, which creates a pressure differential across the lid of the bucket, which produces a driving force that penetrates into the seabed. In sand, it does another, or in sandy materials, it does another thing because you set up a seepage, and this seepage tends to reduce the resistance of the soil, particularly around the tips, making it easier to for the bucket to be installed. I suppose one of the key questions is, well, you come along and you try to do an installation. What happens if you get installation refusal? What mitigation measures can you employ to try to avoid that? You can obviously do things like adding ballast to the top of the bucket to increase the self-weight, but you want to have some other strategies up your sleeve in case that's not quite enough. So one of the potential applications or potential mitigation strategies is something called pressure cycling. This was something we investigated for the sea green development that I mentioned on the last slide, where they were worried that they might not be able to install all of the buckets because the site investigation indicated there was some quite challenging seabed layers that the bucket might not be able to penetrate through. So one of the ideas was that, well, rather than just doing a monotonic pumping, removing water from the interior of the bucket, what you could do is you could pause the pumping and you could reverse it. So what that means is as you pump water out of the bucket is going down. But then if you change the flow direction and you pump water back into the bucket, then the bucket would go back up again. And you could cycle that. So what's happening is the bucket is moving up and down in the seabed. And you can see here, there's a little video playing of this happening in the centrifuge where the bucket is moving up and down as we reverse the flow of water in and out of the bucket. Okay, so why would we do that? Well, if we are moving the bucket up and down, then the soil at the interface between at the skirt of the bucket is being potentially remolded and weakening, and that might reduce the frictional resistance and make it easier for the bucket to be installed. So instead, we've looked at this both for the sea green development, but we also had a PhD student, Sentin Mani, who was looking at this as part of his PhD. And you can see the arrangement he has here in the centrifuge, where we've got a suction bucket connected to an actuator, and then there's a tube, which you can see in this video here, which goes to what we call a syringe pump, which is effectively the pump that is pushing water into and removing water from the suction bucket. His experiments considered a range of soil types, both sand and clay, and in different layering configurations. And we'll look at some of these now in a second. So in this particular case, he was looking at clay, and what we're plotting here is the total pressure. So think about that as the weight of the bucket divided by the area. So we can express it as a pressure. So that's the V on A term, and the P, which is the suction pressure, how much pressure we're applying from pumping. So these, as I say, these installations were in clay. So we're plotting depths on the vertical axes. As I say, we've got this total pressure on the horizontal axis. So we start out and we have a self-weight installation up to around about almost about just over 25%. So this is a normalized embedment sorry, hold on a second. Sorry, yeah, that should be, actually, this is normalized embedment depth. It's not depth in meter, it's normalized embedment depth. So this is a full skirt length. So our self-wind insulation was just under a third of the skirt length. So when we got to that point, then we started pumping, and you can see here this black line here. So there's two tests. So this is a self-wind insulation of just under 0.3 Z on L on one test. And on this other one, we went down further to just over half the skirt length. But in both cases, then we started pumping. And you can see here this black line is a monotonic pumping. So we didn't do any pressure cycling in this case. But in the other case, we did pumping. So this is the blue line and the red line. And we do that, you can see there's a reduction in the required suction pressure to install the bucket. And what that means is that we have reduced the insulation resistance. We've made the soil weaker. If we look at it then, rather than pumping, if we look at it just when we do jacking, so this is in the same soil. So this was the question is it anything to do with the fact that we're pumping, or is it just the up and down cycles of the suction bucket in the sand or in the clay? So in this grey line, we've got a monotonic jacking. So by that, I mean, we're just inserting the bucket. And then in this other test here, we're doing something similar to pressure cycling, but we're just moving the bucket up and down with these jack cycles. And again, you can see this reduction in the insulation resistance. So that tells us that it truly is just the action of moving the bucket up and down in the soil that is reducing the frictional resistance. Okay, so that was a good outcome, but I suppose from a design perspective, you want to be able to predict something like that. So the question is, well, how could I predict that for my particular seabed? So we got to thinking, and we sort of thought, well, it's a little bit like a cone penetrometer test, and we know we do cone penetrometer tests to characterize the seabed. So the question then became, well, what if we did vertical cycles on a cone penetrometer test? Would it be the same? Would it give us measurements that we could use to predict how the suction bucket would perform under pressure cycling? So we give it a go. We have our model scale piezo-cone penetrometer. So it measures cone tip resistance. It measures pore pressure at the cone shoulder, which is the U2 position, and it measures frictional resistance along this sleeve here. What we're plotting here on the left-hand side is a combination of the sleeve resistance, which is FS, and also the remolded under shear strength in this red line. So the remolded under shear strength was established from T-bar test, where we cycled the soil to get down to the remolded soil state, and you can see that that's represented by this red line. And then if we compare the monotonic sleeve resistance, we can see that it's very close to the remolded strength, meaning that cone was rough enough to fully remold the soil on the way in, so that the frictional resistance was remolding the soil. So we're getting a good agreement between the remolded strength from the T-bar test and the cone friction measurements. But then what we did was that we had another test where we cycled the cones. So we're coming in roughly the same sleeve friction, but then we do these cycles when we push the cone up and down and up and down and up and down. And you can see with every cycle, we're reducing the sleeve friction. So we're getting a reduction in the sleeve friction. It's something that we can measure, and then we can compare that with the suction bucket response to see if they are any way comparable. And that's what we're doing on this plot. So what I'm doing is a little bit of a busy plot, but on the vertical, I'll talk you through it. On the vertical axis, you've got a mobilized strength ratio. So that's, in each case, it's either the sleeve friction measured by the cone as a ratio of the intact shear strength, or it's the skirt friction on the suction bucket, again, as a ratio of the intact shear strength. And here we see this. So what are we plotting here? We've got pressure cycles from the suction bucket, which is the tau over SU term. And then we've got this other cyclic cone, which is just the sleeve friction divided by the SU. So that's represented with these circles. And the other tests are pressure cycles, which are either, I think one of them is jacked and the other ones are from reversing the flow with the suction pump. So in the initial cycles, we can see we're mobilizing the remolded strength inferred from a cyclic T-bar, which is what this previous plot showed here. So the friction sleeve and the remolded strength are about the same. So we're roughly starting up around about here. And then with every cycle, we're getting a reduction in the mobilized strength. And what the key takeaway message here is that the reduction and the way it degrades with cycle number is very similar in the cone as it is in the suction bucket test. I suppose another key observation is that if you kept cycling, so in the suction bucket cases, we cycled for about up to 8 or 9 cycles and then we stopped. But in the cone test, we kept cycling, and if you keep cycling, the strength actually hardens again because of consolidation. And that's something that you want to be wary about, because the message here is that if you cycle, yes, you'll reduce the friction, but if you keep cycling, it'll start to harden again, so you don't want to do that. Okay, so sorry, the last thing I wanted to say is that all of that can be fitted with a very simple strength degradation model, which is just shown here, which is just a very simple exponential model, which just shows the degradation in strength with cycle number. You can then incorporate that type of strength degradation model into a prediction model for suction buckets. So here we're just showing an example from the centrifuge where we've got our self-weight installation and then we've got the pumping. So this gray line, it represents monotonic pumping where we didn't do any pressure cycles. We've got the measured in solid gray, and we've got the calculated, which is just a standard suction bucket installation prediction model in this broken line, and you can see we're getting quite a good agreement. And if I then take that simple strength degradation model that I showed you on the last slide, and if I build it into my calculation model, you can then see that you get also very good agreement, or at least very acceptable agreement with the pressure cycled results. So this is an example from the centrifuge. There's also some data from pressure cycling in the field in the North Sea. So again, we have a test where we didn't do any pressure cycling, so that's just monotonic pumping. And you can see it's actually very difficult to see because the agreement between the measured and the calculated is so good. But you can just about see a broken line there overlaying the measured line. If then I introduce the same strength degradation model, and what I want to point out here is that there were no cyclic cones conducted in the field. So we just had to adopt exactly the strength degradation model and the parameters of that strength degradation model that we used in the centrifuge. So there's been no adjusting of parameters, it's just been used as is. And when we do that, we actually are able to capture the reduction in installation resistance or total pressure in this field case very, very, very well. So you can see the black line is the reduction in the response in the pressure cycle test, and this red dashed line is the calculated. So that's showing that indeed you can have a mitigation measure to help you install suction buckets where you encounter a strong layer, and you can do something in your site investigation which will measure that response, and it is something that you can incorporate in a design calculation quite readily. The other thing to point out is that a cyclic CPT is a very simple thing to do offshore. It's not like a dissipation test where it involves lots of time. It doesn't require any differences or any changes to actuation equipment or anything like that. You're effectively just moving the cone up and down, maybe between 10 and 20 times, which might add something of the order of 10 to 20 minutes to the overall duration. So not long at all. Okay, so moving on to another example. This one is on plate anchors in clay. So a plate anchor in clay could be installed either by, if you think about it like a drag anchor, you could drag it along the seabed. That is a very mature technology, but it has some uncertainties because you don't really know where the drag anchor is. So therefore, there's some uncertainty on its capacity. An alternative technique is to locate the plate anchor at the bottom of a suction caisson. You can see this on this photograph on the left. You've got a suction caisson, you've got all of these plate anchors. The plate anchor can be installed at the bottom of the suction caisson, and you use the suction caisson to install it, much as you would with the suction bucket that we just talked about. But afterwards, you would then reverse the pump flow so that you push the caisson out of the soil and remove it from the seabed and reuse it for the next installation, leaving this plate anchor located in the seabed. What's nice about that is that unlike a drag anchor, we know where the plate anchor is, so therefore we don't have any more uncertainty on its capacity other than the actual uncertainty that we have on the strength of that particular seabed. So I would say that the design methods for plate anchors in clay are quite mature and reliable, but one of the things is they don't allow for any temporal changes in soil strength over the design life of the facility. So there may be opportunities for more certain forecasts of reliability if these strength changes are allowed for in design. So we did some experiments again in the in our centrifuge facility here in UWA, where we looked at what would happen if we allowed for such strength changes over the design life. So rather simple experiments, we had plate anchors, just circular plate anchors, which were located towards the bottom of a kaolin clay sample. These were wished in place, meaning that they were located in the sample as the sample was being consolidated. So we're isolating the installation effects. We're just looking purely at capacity. And what we did was that after the sample was consolidated and spun in the centrifuge, we moved the anchor up by about one plate anchor of displacement, so one diameter. And after we did that, we measured a steady state resistance. So you can see this here on the right-hand side. So this is just movement in terms of diameter. So you can see we moved about one diameter, and you can see the anchor resistance is peaking up to a number. And then as the soil softens, it comes down to a normalized resistance of about 10.5, which is a fairly typical number for objects like a plate or a sphere or a bar. After that, we held the anchor either under a fixed position for a period of time, which is the one on the right hand here. So we just told the actuator to hold that position and wait for different periods of time. Or we held a load, and we held different values of load. We held it under either about 15 kPa or 0 kPa. In both cases, we allowed time periods of between about 0.15 hours up to what was our maximum was about 48 hours, so 2 days. And after that period of time, then we started to move the anchor again. So we just told our actuator to move upwards and we to measure the new capacity. And you can see here, we're now just normalizing the anchor resistance by the number that we had at the end of the previous stage, where we moved one diameter and got that 10.5 number. So you can see here, it's all around about 1. So that's the normalized number. And then after each of these consolidation periods, you see these increases. And the increases depend both on whether or not the anchor was held under a fixed position or a fixed load, but more importantly, it depends on the amount of time. So you can see here where you had 0.15 hours, you get a small increase in capacity. And on this one here, the blue one here, where we had a combination of a higher load and the 48 hours, you get in a higher capacity. So like the previous example, we sort of said, okay, those are changes and we could potentially utilize those in design, but only if I've got a calculation method that can capture them. So we started to think about how we might be able to do that. So we said, right, well, what about our T-bar test? So for those that don't know what a T-bar is, it's like the cone penetrometer, but instead of a cone at the tip of the penetrometer, we have this bar. And it's quite a well-established technique for measuring the strength of clay samples. Initially in the centrifuge, and in fact, it started in UWA, but it's also now used offshore. So here we are, we're measuring the strength of our sample, and you can see that you've got these solid lines coming through here. We've got a particular strength. And then there's another test in here, which you can see these little noses. And now, in that particular T-bar test, what we did is we paused. So we inserted the penetrometer, and then we paused, and we waited for different periods of time, and then we continued the penetration, and we get a localized increase in the strength. And here we do another one, and we paused for a longer period of time, and you get a bigger increase in the strength. And then we moved down again, and we paused, and we get an even bigger increase in the strength. So now you can get these localized increases in strength, which, if you think about it, is very similar to what we were doing in the plate anchor test. We were just moving, pausing, and then we were moving again after different periods of consolidation. If we compare the results, so these are a little bit of a busy slide, but we'll just take our time as we walk our way through it. So on the left-hand side, we've got a plot showing dimensionless time. So just think about that as the amount of time that passed during the consolidation. And on the vertical axis, we've got either the normalized anchor or T-bar resistance. So it starts out at 1, and then as it increases beyond that with different consolidation times. So you can see, obviously, the greater the consolidation time, there is a tendency for the resistance to increase. So what are we plotting? Well, the blacks and the sort of the black square, the grey circle, and the blue triangles are all the plate anchor results, and we get a maximum increase of about 60%. And when we look at the T-bars, you see these red crosses are the T-bars, you get a similar increase of about 60%. But then we look at that and sort of try to put some kind of what we call a backbone curve through it, so we can sort of measure the rate at which these capacity changes are happening. You can see there is a difference in the time scale. So yes, we're getting the same 60% increase in both cases, but it's quicker for the plate than it is for the T-bar. And those types of acknowledging that the time scales for those capacity changes to occur are going to be different in the tool that you use to measure them, being the T-bar, relative to the application that you're applying it to, which is being the plate. So yes, you can measure them, but you just need to be aware that there are timescale differences and incorporate that into your methods. I suppose one of the things about doing things in the centrifuge is that you are always at a very small scale. Invariably, you're testing in a soil which is maybe just a reconstituted kaolin. Maybe it's a natural soil, but it's also reconstituted. By reconstituted, I mean that it's broken down into slurry and reconsolidated, so it's lost that inherent structure that natural clays have. So we do tend, or we like where we have opportunities to extend our work from the centrifuge into the field. So we have a soft clay site quite close to us here in Perth, and that we do some experiments at. And when we do these experiments, we're not going full scale because it's too expensive to do something like that. But we do try to step out the scale from what we would look at in the centrifuge. So in our centrifuge, we were looking at anchors that were about 30 to 40 millimeters in diameter. And here at field scale, we're now looking at something that is about 10 times that. So these are 300 millimeters in diameter. It also provides opportunities for having more instrumentation. So now we can get pore pressure sensors, accelerometers to measure rotation. We can measure the load down at the para, etc. So there are other reasons for doing experiments in the field. You can sometimes make measurements that is just too tricky to make in the centrifuge or in any laboratory for that matter. So these anchors were installed to a depth of about 8 meters. So they're actually installed using a cone penetrometer rig. And then afterwards, they were connected up to this actuator, which was installed on a frame. So this actuator was controlled in the same way as we control our centrifuge actuator. So it was really precise, and we could impart quite complex motion sequences. And what we did, I'm just going to look at a couple of tests from the program. There were quite a number of tests, but I just want to look at a couple of them. So what we did is you install them in the vertical orientation, and then you load them vertically, so that you key the anchor. So that means that you take it from a vertical orientation through to a horizontal orientation. And then we left it there for about a month so they could consolidate. And then we came along with our actuator and we applied a monotonic preload. And then we allowed another month of consolidation. And then we came back again and we loaded it monotonically again. And if we just look, and so this is a photograph showing the setup at the soft clay site. On the right-hand side, we've just replotted those results from our centrifuge experiments that we were looking at earlier. So these were the black squares and the grey circle over there, and the blue triangles, and we're comparing that with the field results, those two tests, test 7 and test 8. And if we plot them all at the same dimensionless consolidation time, you can see you're getting actually extremely good agreement with the centrifuge results. And that's important if we really want to see these observations that we make in centrifuge model tests, if we want to see them being taken up by industry, sometimes you really just do have to provide them with the evidence to make it easier for them to take this up. And sometimes that is going out to the field and showing that you get the same result in the field that you do in the laboratory. Of course, that was just monotonic loading. So we have other centrifuge experiments, which actually are from before the ones that I've just shown you, where instead of loading the anchor vertically, we loaded it horizontally. So this is now a vertical anchor being loaded horizontally. But in these cases, in these experiments, we were doing cyclic loading. And they were quite complicated sequences of cyclic loading with consolidation in between. So this just a snapshot. Here we're just looking at displacement, and here we're looking at anchor resistance. So we have 4 tests, and they're all coming in more or less the same steady state resistance. And then there was 4 different types of sequences of consolidation and cyclic loading. And in the case where we had what we call 5 episodes of maintained and cyclic loading, we saw an increase in the capacity by a factor of 2.5. So this is 150% more capacity due to the loading that happens over the design life. And obviously, if that's something that you can incorporate into your design, it allows your design to be much more optimal. Okay, so I think I've got my video for time. I might need to go a little bit more quickly. I wanted to look at, so this was the previous examples were taking existing technology and showing how centrifuge modeling could improve design approaches. And this is where we're using centrifuge modeling to demonstrate or validate new concepts. So the first concept is exactly the same one, the suction embedded plate anchor that we looked at a moment ago. But to date, it's only ever been applied in fine-grained soils, and by that I mean clays and silts. For floating wind developments, you're in much shallower water, which is much less likely to be getting clay. In fact, you're much more likely to be getting a coarse-grained material, or in fact, quite a varied material. So, given the benefits of settlers, can we prove that they're feasible in sands? So we looked at this a couple of years ago. We did some experiments where we first of all recognized that the type of suction caisson that you would use to install a plate anchor in clay would not work in sand, because we know that installing suction buckets in sands, they'd have to be much stubbier, if you know what I mean. So this aspect ratio is now where you've got a skirt length which is roughly the same as the diameter. So if you had something like that, it's much more likely to be able to get into a sand deposit than the very long, slender sort of aspect ratios of 4 or 5 that you might use for a caisson. So we did some proof of concept testing. We took an existing caisson, we took an existing plate anchor, just stuff that we had in the laboratory. We fashioned it together like this. So we put the plate anchor in the inside of the caisson, and it was supported by this insulation brace. The mooring chain went along the outside of the caisson. Because the skirt walls are really quite thin, we had to support that with a skirt tip protector. And we did some experiments in the centrifuge, much like we would have done for a normal suction bucket installation. So this is a video showing the testing. So this is just the self-weight installation. Everything's sped up here. We're now connecting the syringe to the caisson to the syringe pump, so we can do pumping. And now we're starting the pumping, and you can see the bucket is being installed. The installation is complete. We're now closing the valve on the top of the bucket, and then we remove the caisson, and we're now just loading the anchor, and you can see that the anchor is starting to come out of the soil. So that allowed us to measure its capacity. Okay. Again, another bit of a busy slide, but I'll try to talk through it quite slowly. So the first set of experiments was where we had the plate protruding. So the pad eye of the plate was at the same level as the skirt tips. And in this case, this was the first thing I should say, is that all of these figures are showing depth on the vertical axis, and on the horizontal axis, we've first of all got the load that develops on the caisson. The second one is the suction pressure from pumping, and the last one is just the total penetration resistance, which is just the vertical load divided by the area plus the suction pressure. So this is how much insulation resistance does it take to get the thing in. Okay, So first of all, we had to have a benchmark case where we just had a caisson only with no plate in the middle. And in this case, you can see that the load required to get a self-weight installation, we got initial self-weight installation before we start the pumping, and those loads then become constant. And those are quite low values, whereas to get the same initial embedment, you needed to have quite high loads, and that's because of the additional penetration resistance due to the plate. The other thing I should say is that if you can get away with a much lower initial embedment, then you can get away with the lower loads. For example, in this case here, we required 2 kilonewtons to get in about just over, I think that's about 12 millimeters. If we reduce that down to about whatever that is, about 8 millimeters, then you get it's about 1300. And if you reduce that even more to about whatever that is, 4 millimeters, you can get away with about 1000 or 1 kilonewton. So obviously, if you manage to get enough of a seal at those lower self-weight embedments, then you can get away with a lower caisson weight. And then the next slide is showing the suction pressure required to install it. So obviously, the higher the self-weight, the lower the suction. So this pink one, which had the 2 kilonewton self-weight, required less suction. I know, but in all of these cases, they are still requiring more of a suction than the caisson only one, which makes sense because there's more penetration resistance to overcome. And then finally, if we look at the total penetration resistance, you can see that the case with the lowest self-weight also required the lowest penetration resistance, which indicates that actually you may not need all of that high caisson weight to achieve embedment. The other thing you should notice here is that compared to caisson only, you get a reduced embedment, and that's mainly because of the amount of displaced soil caused by the addition of the plate, which means that you have a reduced capacity to fully embed the caisson or the suction bucket. We then did more experiments to say, well, does the plate position matter? So remember in the previous cases, we had the plate protruding at the bottom of the caisson. Now we have the plate hidden back up inside the caisson. And in these cases now, if it's the same three figures, now you can see that you can actually get the load or the caisson weight down quite close to that of just the caisson only. And this is all important because, yes, these experiments show that you can install it, but if it requires a caisson weight or a suction bucket weight that is 5 or 10 times the weight of a normal bucket, then it's just not practical. So if we can get these down to real practical weights of caissons or buckets, then this becomes a practical solution. And you get the same observations as we had before. When you have the lower load, you have a lower overall penetration resistance, quite close to the caisson only case. Okay, so that shows that we can install a plate anchor. What about its capacity? So here we're just comparing plates that are being jacked, which are the green one and the pink one, and we're comparing it with ones that have been suction installed, which are the blue one and the yellow one. And you can see that there's no real difference. This jacked one was just inadvertently jacked to a shallower depth, so it's why the capacity is lower. But all of these other ones don't really show any difference whether or not the installation was a jacked installation or a suction installed installation. That's more easily shown on the right-hand side, which just shows the peak capacity as a function of the embedment depth. And these grey circles show the suction installed ones, and the open circles show the jacked ones. And you can see that they're just lying within the data set, meaning that the suction installation is not actually affecting the capacity. Okay, final example, I'll get over quite quickly, is looking at another way of getting a plate anchor into sand. And in this case, the plate anchor is a helical anchor. So for those that don't know what a helical anchor is, I'm just showing a little video of a couple of divers installing a very small helical anchor that might be used to moor a buoy. It's effectively just a small pile with this helical plate on the outside of it. You can see it here on the right-hand side where they've arranged these helical piles in a group to give additional capacity. They're used onshore for different applications, for example, for supporting transmission towers. They're also used near shore for things like floating pontoons and jetties, but they haven't really been used offshore yet. And one of the things that we do know is that when you go offshore and go to the scale of loads that are required, that offshore wind turbines would require, that it was going to require a massive upscaling of the helical anchor. And the issue with that is that you need a rig, an installation rig that can provide enough torque to install it. Or the alternative is we find some ways of reducing the torque. And that's what I'm going to talk about. So we did, these are very recent experiments. We thought, right, well, what if we jetted or pushed water through the interior of the helical anchor so that it injected water around the helix as it was being installed. The idea behind that is that if we had enough pressure in the water, we would increase the pore water pressure around the helix as it's been installed and weaken the soil. So we give it a go. We developed this modular system. So this is the helical anchor. You can see here the water is being injected at different locations above and below the helix. Here's just a video of it happening in flight. So we've got the in-flight installation. Up here, this is the rotary union where the water is being pushed through. And you can just see it here in the bottom as well. So the water is going through the middle of the shaft. We're starting the jetting whilst we're doing the installation. And then when we're finished, we load the anchor and we measure the capacity. Okay, so what did we say? Let's just plot all of this. So looking at the left-hand side, we have looked at two configurations, one where we had no jets, so just a base case, and the other one where we had jets, which one is that? Sorry, above the helix and at the cone. And what you can see here is, so this is plotting torque on the horizontal axis and plotting depth on the vertical axis. In the case where you had no jetting, you get this torque response here, so it gets to quite high values. But then in the cases where we had jetting above the helix and on the cone, you can see that the torque reduces. And as you increase the flow rate, you reduce the torque even more, or even higher, until you get to a point where it didn't seem to really matter what the depth was. You reach this steady state maximum torque that didn't increase as you penetrated any further. On this figure on the right, we looked at different configurations. So again, we have the black one, which has got no jetting, and then this blue one, which was just jetting at the cone, and then the green one, which was the one I've just shown on the left, which is jetting above the helix and on the cone. And then this pink or magenta one, which is jetting above the helix and below the helix. And this is all for a constant flow rate. And you can see that the best configuration is where you're jetting just above the helix and just below the helix. If we then look at this on the plot on the right-hand side, this is showing how much the torque changes by. So this is normalized torque. So when you have no flow, you're obviously at a value of 1. And as you increase the flow rate, and this is at model scale up to 2 milliliters a second, you can reduce the torque needed to get the anchor in by up to 70%. Okay, so that's all sounds good from an insulation perspective, but then I suppose the question is, what is it doing to the capacity? So what you can see if we look here and just think about these vertical axes as capacities. Don't worry, they're all in dimensionless terms, but don't worry about that. So as the flow rate increases, we do see that we get a reduction in capacity, but it's by 40%. And bear in mind on the previous plot, we can see that the torque reduction was 70%. So that tells us that the capacity reduction is not as significant as the torque reduction. So if we plot a dimensionless capacity to torque ratio, you can see that you get this increase. You get a capacity to torque ratio that's almost doubling as you increase the flow rate. So yes, there is a trade-off that you have lower capacity, but the torque reduction dominates. And what also means is that because the torque appears to be constant with depth, it means you can install the anchor deeper and therefore you can mobilize even higher capacities. Okay, so that brings me to the end and just a few final remarks. I think it's fair to say that offshore wind is the current frontier for offshore geotechnical engineering. It brings lots of new challenges, and there's lots of changes to our design, things like stiffness and non-verticality of offshore wind turbines and things like that. Also, there are opportunities for optimizing design because the implication of or the consequence of a failure is very different compared to conventional energy technology, where you may have people on the vessel. So and also so there's the risk there of loss of life, and also the risk of failure of an oil and gas facility could be a hydrocarbon spill. You don't have those kinds of consequences with offshore wind. I think physical modeling does has a role to play, and I've given some examples showing where we've been able to demonstrate performance for new installation methodologies and different loading regimes, validate new foundation concepts, and also providing performance data that we can use to validate calculation approaches. Physical modeling and the geotechnical centrifuge overcomes some of the limitations of reduced scale testing at single gravity, but there are opportunities to not do this in isolation. I've shown one example where we've also taken this out to the field, providing additional data that just adds weight to the outcomes and findings of our research. And I suppose my final message is that, like anything, we shouldn't use these in isolation, and the path to adoption and industry take-up requires more than a single methodology. And with that, I'll end it there. Thank you.
Thank you. Excellent talk. Professor Loughlin give the physics of the centrifuge modeling and to show some excellent research to demonstrate the contribution of centrifuge modeling to the installation of suction bucket and plate anchor, and also to show the capacity to examine the new concept. Good. There are lots of new information. Thanks again. Okay. Anyone? Oh yeah. Here is in the message box. Now it's time for some questions. If you have a question for the professor, you can open the microphone and ask the question, or also you can text the question in the message box. Anyone?
Hi, Conleth. I'm Kohan, a supervisor by. Can you hear me?
Yeah,
You're quite
I can hear you.
I'm Kehan, supervised by Professor Dong, Professor Wang. And thank you for your talk. I have two questions. The first, the suction bucket is up and down, make it easy to installation, and it will remodel the clay, as you said. My question is about the plant anchor in sand. In clay, the consolidation may increase the resistance, but in sand, in my mind, I think the penetration resistance is higher than the clay. So I think the up and down maybe is more needed in sand, but we cannot use the consolidation to increase the remodeled strings. How to consider this? And
okay. Yeah, I might just answer that question first, if that's okay, because just in case I forget it, if that's okay. So I think what you're saying is that there might be more of a requirement in sand than in clay for pressure cycling, because the installation resistance is going to be higher in sand than in clay. Is that what you're saying?
Yes.
Yeah. Okay, and I didn't show an example from sand, but we do have examples in sand, and it's quite an interesting one because it all depends. And some of the field experience of pressure cycling in sand shows no effect. But we were able to do some experiments where we were also able to show that there was no effect, but that in other cases that there was an effect. And it all depends whether or not frictional resistance or skirt tip resistance dominates the overall resistance. So if you've got quite long skirts and if they're adequately rough, then you're going to develop a lot of insulation or sort of frictional resistance, and the pressure cycling will reduce that in sort of like that sort of friction fatigue phenomenon that we're all familiar with. But if your skirts are actually relatively smooth and they're short, then it's more likely that the skirt tip resistance is going to dominate. And when you do pressure cycling, it doesn't degrade the tip resistance, it is only degrading the frictional resistance. So it all depends whether or not you think that frictional resistance or tip resistance is dominating in sand. As to the bit about the consolidation, I suppose the consolidation aspect is not particularly relevant to pressure cycling in that it's a short-term effect. You're doing everything relatively quickly in an attempt to reduce the insulation resistance so that you can get the thing in. Where consolidation comes in is afterwards, where you've got long periods of time which can change the capacity. So I don't think it's just as relevant to the insulation resistance. But as to the effect of consolidation on plate anchor capacity in the long term, I think we probably need to move away from thinking about clays as being the only soils that where consolidation happens, because the scale of these anchors and foundations offshore is such that even for normal wave periods of 10 seconds or whatever, in the types of sands, and bear in mind, sands offshore are never just clean sands, they're silty sands and sandy silts and things like that. So the permeabilities are generally lower than maybe the sands we look at in our laboratories. So it means that actually you can get either a partially drained or potentially even an undrained response in the sand, meaning that it will behave in a clay from the same consolidation perspective. So there is a potential for consolidation in sandy materials as well as also as there is in clay materials.
Okay, thank you.
You had a second question.
In my first question, I have a confidence is the fractional resistance and the type of resistance can measured in CPT, but I think we cannot distinguish them in the flagship bucket. So I think it's a problem that we make a relationship or link the CPT and the bucket. I don't know.
Well, I guess all that we're saying, in an experiment, you can separate frictional resistance on sort of the load that goes into the skirts and the load that goes onto the lid, because if you're measuring total pressure and pore pressure on the underside of the lid, you know how much load has been transferred there. So then the rest of it must be going to the skirts. So when I produced those plots where I just plotted tau over SU, I could do that because I knew how much of the load was being transferred in as skirt resistance. So if we accept that kind of degradation model, then in fact, all you need to do is apply that in a calculation model. And the calculation model already says, okay, I've got two components of resistance. I've got skirt tip resistance and I've got frictional resistance. So you're just applying the degradation to the frictional resistance. So it's all calculated with equations, and you're just reducing the mobilized strength according to the cycle number. So from that perspective, you don't really need to know exactly how the load transfers. You're just allowing for it in your calculation method. In the same way as if you didn't do any pressure cycling, it's exactly the same. It's just the only thing that you're changing is the mobilized friction. Sorry, the mobilized strength.
Okay, thank you. And my second question is the value of CV. I see your presentation, the one paper 2023, you shown a field date. I don't know how to determine the CV in the field in your picture?
I guess the CV that we used in the field is just the CV that we measured in the field. And you can just, like, it's quite an easy parameter to measure. You can just do a cone penetrometer test and do a dissipation, and you use the dissipation response with a Tain-Hillsby solution or main solution, or whichever one you prefer, to work out what CV is. And that's all that we did when we compared the laboratory test data with the field data. And that's why we do things like work in terms of dimensionless time, because you need to account for differences in the object diameter and also differences in the CV. So the lab data used the CV from the lab, and the field data used the CV from the field. And in both cases, they were just measured in a piece-of-cone dissipation test.
Okay. Thank you.
Did that answer your question, or did I get?
Yes.
Did that answer your question? Okay.
Yes. I got it. Thank you.
You're welcome.
Anyone else? Anyone else have a question for this excellent talk?
Professor, I am a student from Academy of Future Ocean of Professor Dong Wang. I saw a video of Centrifuge in your PowerPoint, and I have a question I'm curious about. The package was upright or vertical at first and later become horizontal with rotation. I would like to ask if the vertical direction of the Earth's single gravity has a greater impact on the stress level or strain level in soil. Can we ignore it?
I think it really depends what the G level is. If you're doing testing at 200 G, then you've got 200 G acting in the horizontal direction, and you've got 1 G acting downwards. So therefore, that component due to Earth's gravity is quite small. If you're doing testing at lower G levels, so for example, some of the work that we do on things like pipelines or on cables, where maybe your model is 20 millimeters in diameter or something like that, and maybe you're only testing at around about maybe 15 or 20 G. In those cases, I think you do need to think about it, but so long as you know what it is and can calculate what the stress conditions are, and also acknowledging that it probably means that your package is not completely horizontal or completely vertical, depending on what way you think about it, then that's okay. So it's you get the same kind of concerns or considerations whenever you do things like testing off the center line on a sample container, because now you've got a stress condition which is quite unusual, because the vector of the centripetal acceleration is not coincident with depth in the sample. It's slightly off. It's not coincident. So I think so long as you're aware of these things and you can allow for them, and you can actually calculate what the effect might be, then that'll tell you whether or not you can ignore it or not. But in most cases, the larger the centrifuge, the larger the radius, the less you have to worry about being off the center line, and the less you have to worry about changes in G level with depth, although that's a trivial thing to calculate, and there's no reason not to do that. It's not an issue to overcome. And the higher the G level, the less important the Earth's gravity is.
Okay, I get it. Thank you. Thank you for your answer.
You're welcome.
Anyone else? We still have time. Okay. I have a little question. Professor, you choose the pressure cycle suction bucket installation. And when you inject water, the bucket will go up and go up and down. I think when this process going there, maybe the water can go along the interface between the inside wall of the suction bucket and the soil. If the water can go through this interface, that means it may be you cannot build up a suction during the installation. I want to ask is the pressure cycle installation will failure sometime later?
I guess there is always the risk that if you pump too slowly, you'll not develop pressure and you'll not develop seepage. You'll just sort of you'll develop seepage. You'll not develop any pore pressure. But I don't think there's any difference between a monotonic pumping and pressure cycling in that regard, because it's the same effect. It's still being dictated by the length of the skirts and the permeability of the skirts. So yes, if you pump too slowly, you're not going to develop enough pressure, and you're not going to facilitate an installation. But there's nothing really different between doing it monotonically and doing it as a pressure cycle. There's no more motivation for the water to try to find its way, along a gap between the soil and the inside interior of the skirt, whether it's been pressure cycled or whether it's a monotonic installation. So I think, yes, there is always the potential for that to occur, but it's as equally as a relevant problem for monotonic as it is. It doesn't become any more onerous or likely when you do a pressure cycled installation.
Okay, thanks. Another question about the helical piles.
Yes.
You show that it's good for the installation of the helical pile by water jetting, but the bearing capacity will reduce. Is there possible to make further consolidation to increase the bearing capacity?
Yeah, it's a good question. We've only really started looking at this because this work is very, very new. Right, the first paper on it is going to be published in NGCF later this year, or in a couple of months' time. We have looked at things where we've done some low-level cyclic loading after installation to see if that could regain some of the capacity. I don't think we've looked at consolidation as such, and in terms of leaving it for a period of time before we load it again. It is something certainly we could look at. But I suppose our main thinking about it is that, yes, you still get a reduction in capacity, but the reduction in capacity is so much lower than the reduction in torque, such that the torque is, the reduction in torque is always going to be the winner, because it means that you can install an anchor much deeper where it's going to have more capacity anyway, even if it's reduced by 40%, because of the relative to a non-jetted case, the fact that you may be able to get it in twice as deep means the capacity is already doubled, and then it's reduced by 40%. So it's still going to win out. Obviously, if there was things that we could do to get that capacity back again, that would be good. As I say, we did look at some low-level cyclic loading to try and get some densification happening. That had a very small effect, nothing particularly beneficial there. Yes, maybe consolidation would be something that we could look at. But I think regardless, even if it's something where we can't get it back, it's still worth doing, because you're getting a higher capacity by virtue of the fact that you can get deeper, or that you're not that the installation depth is not limited by the amount of torque that would be available on an installation rig.
Okay, thank you. Okay, anyone else had questions? If there is no further question for the professor, let's thanks again for the excellent talk. And it's our honor to have you here, and we hope you in the future sometimes you have the opportunity to visit the group of Dongwang in Qingdao, and we hope also have the opportunity in the future to visit the NGCF. Thanks.
Lovely. Thank you very much. Appreciate it.
Thank you.
All right.
And
Goodbye.
bye-bye.